Today I'm going to be discussing the idea of areas of cross-sectional areas. So we're going to graph some function, let's just say um, y equals 6. We have this we're going to have y is equal to 6. And we have another function, which is a natural log function, but we're going to have it be going like this. The x inside is negative, so it's going to be doing something like this. And it intersects the x-axis at is equal to 2. Let's not do that. Let's do this in yellow. 2. So we have these functions here, and this is going to be a y is equal to 4 ln 3 minus x. So we have these two functions here, and we're going to look at the concept of cross-sectional area. So you have this little distance here between these two curves. But instead, what if we drew this I'm going to draw a kind of three-dimensional figure here. So we have our x equal 2 line. So this is our x-axis. I'm kind of rotating it on its side to an extent. So we have this x is equal to 2. Not x is equal to x. X is equal to 2. And we have our y is equal to 6 line up here. So y is equal to 6. And so we can kind of graph this function again. I'll do it like that. And so if we wanted the cross section right here, we could do that. And so we want to sometimes find the volume with a square cross section. So let's draw a square cross section right here. And so the idea is whatever this width is, this y minus x, the 6 minus this other function here in this case, this distance, we're going to go with that distance in the air. And then let's draw one over here. So this distance, this is at y equals 6, so this is going to be 6 units up. And then we're going to draw a square. And these aren't two-dimensional squares, we're doing volumes here. So when we integrate, the idea is that we sum up tiny little dx's. And in this case, we have our areas. We can find this area, but we also want to find some little dx. So if we go from here to here, you can imagine that this is a very tiny tile with width dx. And we're going to sum up all of these tiny tiles, and it's going to create a beautiful shape that looks something like this. If I drew another tile that connected this, it's going to look something like this. Isn't it beautiful? And so we want to find the area of a singular tile and then integrate that from the first bound of integration to the end. And we know how to do that. We can find the area of this tile. This is our tiny little dx here. This side length is just the top function minus the bottom function. We know how to do that. We can find these tiny little areas. So let's integrate and go from our bounds of integration. This is x is equal to 0 here to x is equal to 2. And then we want to sum up these tiny, instead of areas, we're going to do these tiny volumes. So the thickness of our rectangle is dx, and one side length is, in this case, 6 minus our function value, which is 4 ln of 3 minus x. This is not squared. 3, come on now, 3 minus x. 3 minus x. Now this is one side, so I was thinking ahead here. We want to square this, because this is one side, and to get this area we need to square it. And then to find the volume we multiply it by dx. And we can just integrate this. And this is the problem that you would probably do in a calculator, or just say write but do not solve, or something like that. This is the introduction to a cross section. Alright, let's go do another one. Let's do some semicircles. So I'll do this in white. So we have our x and y axes here, and we're just going to plot a line, and this is just 1, 1. This is x plus y is equal to 1. Let's draw a picture of what we want this to look like. Let's do this instead with semicircles. So we're gonna draw another one. I'll draw this line in yellow actually, oh, just to, is that 1, 1, and y plus x is equal to 1. And then let's draw another one, but we're going to rotate it slightly. So we have our little thingy and our line. This is the exact same thing, just rotated so we can kind of sketch this in 3 dimensions here. So this is 1 in the x direction and 1 in the y direction. This is 1 in the y direction. And so we want to create semicircles here. And we're going to do this perpendicular to our x-axis. So let's draw some semicircles. I'll draw a semicircle here. And we're going to do this like this, so that this is y by 2. This is y by 2. Whatever this is, for any semicircle that we draw, this is y by 2. Because it's a semicircle and we want this to be in the middle. So let's draw another one to just kind of demonstrate this volume. So we're going to kind of go up from the middle, draw our semicircle. That kind of looks like a triangle. But then we can draw this and we can kind of shade it a little. My incredible, legendary, oh, legendary drawing skills. But I think you can kind of imagine this with me. That we're going to have these semicircles here. And so just like the other one, we want to first calculate the area of one of these, and then we can just say, what about just the volume, assuming that it's about the same with a very tiny dx. dx. So let's calculate this area first. So we know that this area is, the area of a circle is pi r squared. The area of a circle is pi r squared. Pi r squared. But this is a semicircle, not a full circle. We're just looking at one side, so we're going to say pi r squared over 2. But again, the radius is y by 2. The radius is y by 2. So the area is actually pi. I'll pull up the pi by 2. And then we're going to say y by 2 squared. Y by 2. The quantity squared. Because the center of the circle is at y by 2. No matter which x value we're at, no matter what y value we're at, the center of the circle is at y by 2, and we start it from there. So we have to say y by 2 squared. So let's actually write this and our y value in terms of x to get something we can integrate. So let us solve for y. Y, we just subtract x from both sides, is equal to 1 minus x. So now we have now we can find an area function. Now we can find the area in terms of something we can integrate. So that's pi by 2. Pi by 2 times 1 minus x all over 2. And all of that whole quantity is squared. And so if we wanted to find the total volume of this drawing thing, this semicircle creation, we just integrate and sum up these tiny little volumes. So we know that this, oh, this is at x equals 0, and I told you that this is at x is equal to 1. And so we can pull out this pi by 2 because it is a constant coefficient. So we can just pull out this pi by 2 out front, and we can just integrate 1 minus x over 2, the quantity squared. Now we need to find the thickness of these rectangles. We have to multiply by the thickness, which is dx. This whole quantity is squared. And so this is something you could evaluate. You don't even need a calculator. You can expand this binomial, or you could probably do some kind of u sub. But this is something we can integrate. Now I'm going to do the same thing, but with an isosceles triangle. So I just have two generic functions, so we can kind of derive this without thinking of numbers exactly. But we have our x-axis here and our y-axis. We have a function f and g. And then we can solve for the area between these two curves at one particular point is this f at that point and the g at that point. So let's just call this height h. So f of x minus g of x, g of x is equal to h of x. So we can find this height that does not really look like an h. H. And we're going to do isosceles triangles. I know this looks like a triangle anyway, but we're going to have our three-dimensional cross-section be a triangle. So we're going to draw our x and y axes so we can just kind of look at this and imagine it to an extent. And so we have our point, let's call this A, where they intersect, and point, I guess, B over here, where this function intersects or I guess where either they intersect at some point B and over here. Let's try that again. Uh, Actually, I'm going to undo that. I'm going to say B is over here. this is our point B. B. So let's draw our little line here. And so this is our point B. And this is some point C, I guess. So now we want to start drawing some equilateral. Let's do isosceles triangles. I think I said that. So, and you can kind of derive these with other triangles too. I'm just going to show the isosceles one. So here is a singular isosceles triangle that is jutted out, and let's do another one. And so isosceles triangles means that these two angles are the same, and these two sides are the same. And let's do an isosceles right triangle to just make our math easy. So we have side 1, and these two sides are the same. This is a isosceles right triangle. Isosceles meaning two sides are the same, one side is isolated. It's so close to being an equilateral triangle, but this side is isolated. It is an isosceles triangle. So, because this is a isosceles right triangle, these two angles are 45 degrees. And so we can find the relationship if we call this height h, and we have to find an isosceles right triangle, the other sides of this right triangle. We know that if this side is h, and this is a right triangle, we can do our sine and cosine identities. So we can say at this angle, the sine of that this is a over b is just square root 2 over 2. Square root 2 over 2. The sine of 45, or the sine of pi by 4, is square root 2 over 2. And then for this one, we could say the cosine of 45 degrees, or the cosine of pi by 4 radians, is square root 2 over 2 times h. Because, again, these are 45-degree angles, and so the sine is this one, and the cosine is this one. And we can do this because these are right triangles. We really want to try and find the area of this. So I'm going to use a Pythagorean theorem here, saying that this side squared plus this side squared is equal to this side squared. And because these two sides are the same, you can just say that this is another way if you don't know your trigonometric identities, which you should know, but if you don't know them and are just blanking on your test, we can call one side A. So let's say A is just one side of this that is not H. We just call this A, and we can square it. And because they're both the same, they're just A squared, again, is equal to H squared. This is just 2A squared is equal to H squared. 2A squared is equal to H squared. And we want to solve for the side length. Want to solve for the side length here. So we do our inverse PEMDAS. We divide by 2. So that's h over 2, or h squared over 2. And then we take the square root of both sides, and that is equal to a. And so what we can do is we can break apart the square root, saying this is just h over square root 2. But hey, we've solved for a, and it doesn't look like this. Well, we can just rationalize our denominator here. Square root 2, square root 2. So this just becomes 2 on the bottom, and this is just square root 2 over 2 times h. And so that's just another way of solving it if you don't know your Pythagorean identities. But we want to find the total area. I'll do that as capital A. Labeling the multiple things A is probably not a good idea. So let's actually rename this point, or just like delete it. Well, I'll keep it. Let's call this point Z. We're not going to use Z. This is point Z. So the total area of this each triangle will be, let's see, we want to, the area of a triangle is 1/2 base times height. We want to try and find the height of this rectangle. But do you want to know something incredible about right triangles, or 45-degree triangles? Come on. Okay. So this is 45-degree angles. We cut this in half. This is another 45-degree angle. So that this and this now must be the same. This is h by 2, and this is h by 2. So it's just 1/2, and both b and h are square root 2 by 2. So 1/2, this is square root 2 by 2, and this is square root. You could also think of it a bit better this way. This is the base, this is the height. They're both square root 2 by 2. I'm slow, that took me way too long. Square root 2 by square root 2, then all over 2 times 2. You would have actually got, and then h, and then h. You would have gotten the same thing if you had done this with the h by 2 times h by 2 times 1/2, because these square roots cancel, leaving 1/4 h squared. And then you can integrate this from where they intersect initially, or where you want to start, or whatever. Let's actually finish up my sketch, because I didn't do that. Draw another triangle. There we go, and then we could shade it. Very epic. And then we're going to just go down where they meet. So we could go from point Z to point B. And then we can pull out our 1/4. And this is h squared, is what we have left. And h is f of x minus g of x. So we can just do our f of x minus g of x, the quantity squared. And we are doing tiny little volumes here, so we have to multiply by dx.